Have you ever noticed how quickly your phone's assistant responds when you ask a question? Or maybe how effortlessly your smart doorbell identifies, a package arriving?
Yeah, it often feels almost instantaneous, doesn't it?
It really does.
Yeah.
But have you ever paused to consider what's really happening behind the scenes? Like what makes that possible?
Or perhaps how quickly artificial intelligence is evolving beyond those huge, massive cloud-based systems we usually hear about.
Exactly, because that world, the AI world, it's really in the middle of this uh, profound strategic change right now.
That's a truly insightful way to put it. We're seeing a major shift away from relying only on those enormous centralized models living in distant data centers.
And moving towards something totally new.
Towards an entirely new paradigm, really. Think smaller, decentralized, and highly specialized AI that operates right at the edge of the network.
Right on your device, maybe.
Exactly. Inside your smartphone, or on a local server in a busy factory, or even embedded directly within a robot. It's not just a little tweak, it's a fundamental re-architecture.
And that's precisely what we want to unpack today. For this deep dive, we've really dug into an incredibly insightful expert paper by Rick Spare. It's called Edge-Capable LLM Ecosystem Evolution. And we've pulled out the most critical insights, the really surprising facts, just for you.
Yeah, this source, it really lays out the foundational shifts and the cutting-edge tech that's fueling this whole revolution in how we deploy AI and how we experience it.
So our mission today is to figure out why this shift to edge AI isn't just, a technical curiosity or some minor optimization.
It's actually becoming an absolute necessity, a strategic imperative, really, driven by a mix of economic realities, performance needs, and crucially, privacy.
Okay.
So we'll explore the innovative technologies making it all possible and, importantly, what it means for everything, from the future of smart factories to your personal privacy and the next generation of intelligent devices you'll be using every single day.
Okay, let's truly dive in. So let's start with this idea, this compelling idea you mentioned, that the era of the AI monolith, this single giant centralized brain, is actually fading.
It is.
It really does feel like we're stepping into an age of distributed intelligence. What does this strategic pivot away from those huge general-purpose cloud models really mean for AI?
Well, what's truly fascinating, I think, is that it points to a significant maturing of the whole AI market. For a long time, the narrative was always about building the biggest, the most general AI models possible, especially large language models, LLMs.
Right, bigger was always better.
Bigger is better, and stick them exclusively in the cloud. Rick Spare's paper highlights that this very era, where that monolithic cloud-bound LLM was seen as the only real solution, is now actively giving way.
So it's not just a minor adjustment.
No, it's a strategic reorientation of how AI is going to operate in the real world, a really fundamental shift.
So it's not just about making models smaller just for the sake of it then. There's a much deeper, almost unavoidable strategic need driving this.
Absolutely. This transition towards smaller, more agile, efficient, and importantly, more secure ways of doing things centered on small language models, SLMs, running right at the network edge. It's being forced by this powerful combination of things.
Like what specifically?
Economic pressures, for one, critical performance requirements like speed, and, an undeniable demand for privacy.
Okay.
The old way of always pinging these powerful AI brains purely in the cloud is being challenged by a new way where AI capabilities are brought much, much closer to where the data is actually generated.
And where the action happens.
Where actions are needed, yeah. Think of it like pushing intelligence right to the front lines.
That makes a lot of sense.
Yeah.
Okay, to make sure we're all on the same page, let's clearly define these terms.
All right.
Because I think a lot of people just hear LLM is big, SLM is small. What's the precise difference?
That's a really crucial distinction, and the paper clarifies it nicely. So large language models, LLMs, they're defined by their immense scale. We're talking parameter counts from hundreds of billions up into the trillions.
Wow.
Think models like OpenAI's GPT series, right? They're trained on absolutely gargantuan, incredibly diverse data sets scraped from the public internet. Just vast amounts of human knowledge.
So their strength is versatility.
Exactly. Their superpower is sheer versatility. They can handle a huge range of general-purpose tasks, generating creative content, summarizing complex stuff, intricate reasoning. They really emulate a very wide-ranging kind of human intelligence.
But there are downsides.
Oh, yeah. Big downsides. This generality comes at a cost. They need massive computational resources, usually vast GPU clusters in the cloud, which means high, often unpredictable operational costs, huge energy consumption, and performance limits like increased latency, especially when lots of people are trying to use them at once.
Okay, so if an LLM is like this super smart generalist, incredibly knowledgeable, but also expensive and maybe a bit slow sometimes,
Yeah.
what exactly is an SLM then?
Precisely. Now, small language models, SLMs, are on the other side of that spectrum. They have a significantly smaller parameter count, usually a few million up to maybe a few billion, typically staying under 40 billion parameters.
Faster, smaller.
Much smaller. But here's the absolutely critical part, and this is where people get it wrong sometimes. They aren't just scaled down, less capable versions of LLMs.
Ah.
True SLMs are often specifically trained or, more commonly, fine-tuned on smaller, highly curated, domain-specific data sets.
So they're specialists.
They're specialists.
Right.
This allows them to achieve very high precision and efficiency on a much narrower set of tasks. Their big advantages are efficiency, way lower resource needs, lower cost, and much faster inference speeds.
Which makes them perfect
for deployment on resource-constrained hardware. Your smartphone, a smart camera, embedded systems right at the network edge.
So the real value of a true SLM isn't just its size, it's that laser-focused expertise, right? Like a highly specialized surgeon versus a general doctor, brilliant in their niche.
Exactly. That's a great analogy. A smaller model trained generally might just be, well, a less capable generalist. A true SLM, though, is optimized for its niche, delivering superior, sometimes even unmatched performance within that specific domain.
We can really see this if we compare them side by side, can't we?
Definitely. The key characteristics tell the story.
Okay, let's break that down. If we look at parameter count, you said LLMs are hundreds of billions to trillions. SLMs are millions to a few billion, typically under 40 billion. That's just a massive difference in scale.
It's huge, and that directly impacts their training data. LLMs gulp down vast general internet stuff. SLMs are fed smaller, curated, domain-specific data sets.
And this focused training shapes their scope and capability.
Yeah.
LLMs are general, versatile, broad. SLMs are specialized, high precision on narrow tasks.
Exactly, which then leads to resource consumption. LLMs need those massive GPU clusters in data centers.
Right.
SLMs, low to moderate needs. They can often run on a single server, a local gateway, or even run on the device itself. That's a total game changer.
Yeah. Which then affects their inference speed and latency. LLMs have higher latency, maybe get slower with more users.
Yeah, often they do. SLMs, though, offer extremely low latency, often real-time capable, meaning they can respond in milliseconds.
Okay.
This also dictates their deployment model. LLMs, mostly cloud APIs. SLMs, on-device, edge server, embedded right into the system.
And the operational cost just follows that logic.
Yeah.
LLMs are high, ongoing costs. SLMs are typically low, more like a fixed investment.
Right. And finally, their ideal use cases really highlight the difference. LLMs are great for general chatbots, creating broad content, research. SLMs shine in industrial automation, personalized on-device assistance, specialized medical diagnostics.
Yeah, maybe the most critical difference for many people and industries, privacy and security.
Absolutely. With LLMs, there's often a higher risk because you usually have to send sensitive data to a third-party cloud.
Which people are increasingly wary of.
Very wary. With SLMs, privacy is inherently higher because the data typically stays local, on the device or server, under your control.
That distinction really hammers home why this big shift is happening. So, beyond just the tech specs, what's the bigger strategic reason for this push to miniaturization? Why does this matter so much, both to industries and, to us?
This is where those strategic imperatives really sharpen into focus. The industry's pivot towards these smaller, edge-capable models isn't random. It's being pushed by 4 very clear, very compelling drivers that directly tackle the inherent problems with the old centralized LLM way.
Okay, let's start with the money. Economic viability. That seems like a pretty obvious driver.
It absolutely is. Running LLMs at scale, the operational cost is colossal. It creates this prohibitively high barrier to entry for so many organizations.
So only the big players could really afford cutting-edge AI.
Pretty much. SLMs, by dramatically lowering both the upfront investment and the ongoing operational costs, effectively democratize access. They make powerful AI much more affordable.
Which opens the door for more companies.
Exactly. It makes a much wider range of specialized applications economically feasible for businesses of all sizes, from nimble startups to established players.
Then there's performance, specifically latency and reliability.
Yeah.
You mentioned this earlier. If you're talking about a self-driving car or a critical factory robot, you just can't wait for a signal to go to the cloud and back.
Precisely. Real-time applications, whether it's controlling an autonomous vehicle, the split-second timing needed by industrial robotics, or truly interactive AR, they just cannot tolerate the variable latency you get with cloud round trips.
Network issues, server load.
Exactly. It can kill performance, making a purely cloud-based LLM totally unreliable for mission-critical stuff. SLMs running locally, though, they provide consistent, low-latency inference. That's absolutely essential for these things to work safely and effectively, often sub-millisecond responses.
Huge difference.
Huge. It translates directly into safety and efficiency.
And privacy and security, this feels like a massive one today, especially with regulations like GDPR and OIPA.
It's paramount, and it's a major drawback of the centralized model. Training and running traditional cloud LLMs often means sending sensitive user data to third-party servers.
Which is risky.
Hugely risky. It creates privacy risks, security vulnerabilities, and big compliance headaches, especially in regulated fields like healthcare or finance. On-device processing with SLMs fundamentally changes that.
How so?
Sensitive data stays local. It remains under the user's direct control. That drastically cuts down those risks and makes regulatory compliance much, much simpler. It's a huge step for data sovereignty.
Okay, finally, let's talk about personalization and context awareness. How does an on-device SLM make AI feel genuinely personal, truly aware of my specific world?
This is an incredibly powerful driver. The best user experiences today are deeply intuitively personalized, right?
Yeah, definitely.
An on-device SLM can be safely and continuously fine-tuned using an individual's private data. Think your emails, messages, calendar, sensor data from your device.
So if you never want to send to the cloud.
Exactly. This allows it to create a truly context-aware, uniquely personalized assistant that understands your habits, your preferences, your information. Achieving that level of deep personalization is basically impossible, or at least ethically fraught, with a centralized cloud model. Aggregating that kind of sensitive data from millions is just an unacceptable risk.
So it's about making AI truly yours.
Precisely. Truly yours, truly private.
So this strategic shift, it's not just about smaller models. It's fundamentally changing how AI gets built into our lives and industries. It sounds like we're moving from just accessing AI to actually embedding it right into products.
That's a perfect way to put it. The early dominance of LLMs set up this model where AI was mostly a feature you accessed via an API, usually from one of the big tech providers.
Kind of like plugging into the mothership.
Kind of, yeah. And that centralized power inherently limited how deeply AI could be integrated. But the rise of SLMs enables this crucial transition. AI becomes an embeddable component.
So companies aren't just connecting to AI.
They're building AI into their products directly. This totally changes the business model. It empowers a much wider range of companies to become creators of truly AI-native products, not just consumers relying on someone else's service.
And the paper predicts this could lead to, what was the phrase? A Cambrian explosion.
Yeah, a Cambrian explosion of new, specialized, intelligent devices and applications that just weren't economically or technically viable before. It's like a burst of new, intelligent life forms appearing in the tech ecosystem.
That's a fantastic image. So does this mean the cloud is like dead for AI? Or is the future more of a mix using what you called the LLM supply chain?
It's definitely not a binary choice. The paper strongly emphasizes this. The future of AI architecture is absolutely a hybrid one. The most effective strategy will cleverly use the strengths of both the cloud and the edge.
So the giant models still get built in the cloud.
Yes, those massive general-purpose foundation models will keep being developed and trained in the cloud because that's where the truly vast computational resources are available for those huge initial training runs.
Okay, and then what happens? How do those cloud giants connect to the edge specialists?
Then, smaller specialized SLMs are carefully crafted from these cloud-trained foundation models. This happens through powerful techniques like knowledge distillation or fine-tuning.
Right, like the teacher-student model you mentioned.
Exactly. And then these optimized SLMs are deployed out to the edge. This whole process, what we can call the LLM supply chain, taking a powerful base model, running it through compression and specialization to generate a portfolio of edge-ready SLMs that will become a core skill, a core operational competency for any leading tech organization.
So it's about optimizing the whole journey of intelligence, from cloud birth to edge execution.
Perfectly said. Optimizing that journey.
Okay, so we've explored this major strategic shift, defined the key players LLMs and SLMs. Now, this whole pivot towards distributed intelligence relies on some really fascinating new architectural approaches. This is where it gets really interesting, looking beyond just that single central brain.
Indeed. And it's all about overcoming the inherent weaknesses of purely centralized AI.
Let's touch on those problems first. Why are traditional, mainly centralized AI systems actually kind of vulnerable? Why is this idea of distributed resilience becoming so important?
Well, the traditional setup where you have one main server or maybe a tight cluster of servers acting as the central brain, it has several built-in weaknesses. First, it's a single point of failure.
If it goes down, everything stops.
Everything stops, dead in the water. Second, they hit scalability bottlenecks pretty hard. A central node can easily get overwhelmed as the load increases, leading to frustrating slowdowns.
Yeah, we've all experienced that.
We have, but maybe most critically, this model concentrates immense power and often very sensitive data in the hands of just a few companies or entities.
Creating data monopoly.
Creating data monopolies, yeah, and posing significant risks related to privacy, potential data misuse, even censorship. It's a structure that can be brittle and, frankly, quite problematic when you scale it up, especially with today's data volumes and sensitivity.
So to fight that, we're seeing this fundamental move towards decentralized and distributed systems. How do these new approaches actually work? What are they?
Right. In response to those weaknesses, two main alternative paradigms are really gaining steam. First, you have decentralized systems. In these architectures, control and computation are spread across multiple independent nodes. Crucially, there's no single central authority.
Each node is kind of its own boss.
Pretty much. Each node operates autonomously but collaborates with others to achieve shared goals. This structure is inherently more resilient, more fault-tolerant, because if one node fails, the whole network doesn't collapse.
Like P2P networks or blockchain.
Exactly. Think of foundational tech like peer-to-peer networks or blockchain. They're great examples of these robust, often censorship-resistant systems.
Okay, and then there are distributed systems. Is that different from decentralized?
It's a slightly broader category. In distributed systems, computational resources are spread across multiple physical locations, but they often work together as a single, unified system, typically under some form of shared or coordinated control.
Like a big company with many branches, but one HQ.
That's a good analogy. The emerging edge computing ecosystem with its layers of devices, local gateways, regional servers is a prime example of a distributed system. Both decentralized and distributed structures effectively tackle the limits of centralized control and really lay the groundwork for a more robust, more private, and more scalable AI ecosystem.
And within this new landscape, federated learning, FL, seems like a real cornerstone technology. It's described as the engine of collaborative private AI. How does that actually work? It sounds almost like magic.
Federated learning is truly a powerful technique that operates within these decentralized or distributed setups, and its core idea is revolutionary. It lets you train models on data that's spread across many devices or servers without ever bringing the raw data together in one place.
Okay, that's the key. No central data pod.
No central data pot. It directly solves that fundamental conflict we always face. Needing diverse data for good models versus needing to protect user privacy and data sovereignty.
So the sensitive data literally never leaves the device. That sounds almost too good to be true, given how much data AI usually needs. Can you walk us through the workflow step by step?
It's actually quite clever. The most common FL workflow, which usually involves a central coordinating server, goes like this. First, initialization. A central server starts things off with a global AI model.
Okay, it's starting point.
A starting point. Then, distribution. A copy of this global model gets sent out to a selected group of client devices, could be smartphones, hospital servers, factory sensors, whatever.
All right.
Now, the real magic happens during local training. Each client device trains the model only using its own local private data. So your phone uses your interaction data. A hospital uses its private patient records all securely within its own walls.
So they're all learning individually on their own private stuff. But how does that help the global model if they never share the actual data?
That's the crucial privacy-preserving step, update transmission. After the local training, each client sends back only the learned model updates. These are essentially the changes made to the model's parameters, its weights and biases.
Not the data itself, just the learnings.
Just the learnings. The sensitive raw data never leaves the client device, stays right where it is. Then comes global aggregation. The central server collects these updates from all the participating clients.
And combines them somehow.
Yeah, a common method is federated averaging. It calculates a weighted average of all the client updates to produce an improved, more generalized global model.
And then it just repeats, getting smarter each time.
Exactly. The iteration step repeats. The newly improved global model gets sent back out to clients for the next round of training. Over many rounds, this global model keeps converging, keeps improving, benefiting from the collective wisdom of all clients without ever seeing their private data. It's a virtuous cycle of distributed private learning.
That's really neat. Are there different flavors of FL for different situations?
Yes, it's quite adaptable. You have cross-device FL, which usually involves tons of potentially unreliable, low-power clients like mobile phones. That's great for consumer apps.
Right.
Then there's cross-silo FL. This involves a smaller number of highly reliable, powerful clients like a group of banks or hospitals collaborating.
Makes sense.
We also differentiate based on the data structure. Horizontal FL is when clients have the same kind of data features but different examples, like two hospitals with different patient groups.
Right.
And vertical FL is used when clients have different data features, but for the same set of users, like a bank and a retailer, sharing insights about the same customers without sharing all their data.
This sounds amazing for privacy, but you mentioned LLMs earlier. They're huge. How on earth is it possible to train or even just fine-tune multi-billion parameter models on a typical edge device using FL? That sounds like it would melt my phone.
It was a massive hurdle, you're absolutely right, until a real breakthrough made it practical. Parameter-efficient fine-tuning, or PEFT techniques. The most famous one is probably LoRa, which stands for low-rank adaptation.
LoRa. Okay. How does that help?
The core problem with FL and giant LLMs is exactly what you said, the computational impossibility of training billions of parameters locally on a weak edge device. With LoRa, instead of trying to fine-tune all those billions of parameters,
You do something else.
you add a very small number of new trainable adapter layers to the model. Critically, only these tiny adapter layers are trained locally. The original massive model weights stay frozen, untouched.
So you're not trying to reshape the whole giant statue, just adding tiny trainable clay ornaments.
That's a perfect analogy, exactly. This drastically cuts down the compute power needed for local training. And just as vital, it shrinks the size of the model update you need to send back to the server. Instead of potentially gigabytes of changes, it's down to mere megabytes.
Wow, that's huge.
It is. This breakthrough is what makes federated fine-tuning of large language models on constrained edge devices not just a theoretical idea, but genuinely feasible and efficient in the real world.
So federated learning isn't just some clever tech trick. It's almost a necessary response to things like GDPR or iPay. The paper even calls it a technical safe harbor.
That's absolutely spot on, and it's a key strategic point. The rise of FL isn't just tech evolution, it's a direct market response to the growing pressure from global data privacy rules.
Because the old way is becoming untenable.
Exactly. The traditional central approach of gathering huge amounts of user data for AI training, it's becoming legally risky and bad for your reputation. It creates massive compliance burdens and, let's face it, a giant, juicy target for data breaches.
Right.
Federated learning offers this technical safe harbor because, by its very design, it sticks to core privacy principles like data minimization and purpose limitation. The raw, sensitive data never leaves its source, the user's device or the hospital's secure network. Only the abstract math learnings, those non-sensitive model updates, are shared.
So it aligns technology with regulation.
Perfectly. And that alignment elevates FL from just an engineering choice to a fundamental C-suite strategic decision for managing risk.
This sounds like it creates a really powerful positive feedback loop.
Yeah.
The paper calls it a decentralization specialization flywheel. Can you unpack that virtuous cycle?
It's a really elegant concept that captures the synergy here. So having powerful, specialized SLMs available makes decentralized applications much more compelling, right?
What?
For instance, a medical diagnostic SLM is most effective when it's personalized with a patient's private data. That inherently requires a private, on-device, decentralized setup.
Right.
Now, these decentralized systems, because they're private and personalized, generate unique, high-quality data streams that are naturally siloed across many devices or institutions.
So you have all this valuable but separate data. How does FL connect it?
Federated learning provides that ingenious bridge. It lets you tap into this distributed data by aggregating the learnings again, not the raw data, to train an even better, more accurate global model, all without breaching privacy.
And that improved global model.
Gets pushed back to the devices, making the specialized SLM on your phone or in that hospital even more powerful and accurate for your specific needs. This creates the virtuous cycle. Better specialization drives the need for decentralization,
Which enables private data collaboration via FL.
which leads to even greater specialization and better model performance. It's a self-reinforcing system that constantly improves, pushing intelligence further and further out to the edges.
That's really elegant. Okay, so we get the big strategic shift. We understand the architectural changes like FL-Bell making distributed intelligence feasible. But how do we actually shrink these monster models and make them run efficiently on tiny little devices? This brings us to the core enabling technologies, the actual toolkit for on-device smarts.
This is indeed where the rubber meets the road, technically speaking. This whole transition to a distributed, edge-native AI world is only possible because of a powerful convergence of deep tech innovations. We can basically group them into three main pillars:
Okay, what are they?
model compression, architectural innovation, and hardware-software co-design. Getting good at these is absolutely essential for putting sophisticated language models onto those resource-constrained edge devices.
Let's dive into model compression first. You called it the art of algorithmic miniaturization. How do you shrink a giant AI brain without making it, well, dumb?
Right, that's the challenge. Model compression is really a suite of clever techniques designed to significantly cut down the memory footprint and the computational needs of a neural network while trying really hard to minimize any hit to its accuracy.
Which is critical for LLMs on the edge.
Absolutely critical, given their starting size. The goal isn't just smaller, it's smaller and still smart.
So what are the main tools in this compression toolbox? I've definitely heard of quantization.
Quantization is one of the most effective and widely used methods. Basically, it involves reducing the numerical precision of the numbers used in the model. That includes the model's parameters, its weights, and sometimes the intermediate calculations called activations.
So instead of high precision numbers.
Exactly. Models are usually trained using high-precision 32-bit floating point numbers, FP32. Quantization converts them to use lower precision formats like 16-bit floats, FP16, 8-bit integers, INT8, or even tiny 4-bit integers, INT4.
And the benefit?
Smaller memory footprint, definitely. Lower power consumption. And often much faster computation, especially if the hardware has specialized units designed to handle these lower precision numbers efficiently.
Are there different ways to actually do the quantization?
Yeah, two main approaches. Post-training quantization, PTQ. You apply this after the model has already been trained. It's simpler to do, but sometimes you might see a small drop in accuracy.
Okay. And the other way?
Quantization-aware training, QAT. Here, you simulate the effects of quantization during the training process itself. This lets the model learn to adapt and be robust to that lower precision.
So QAT usually gives better accuracy.
Typically, yes, but it's more complex and needs access to the original training data and more compute resources for that training phase.
Okay, what about pruning? That sounds like you're literally chopping bits off the model.
In a way, yes, but strategically. Pruning aims to remove redundant or non-essential parts of a trained neural network. By identifying and eliminating parameters that don't contribute much to the final output, pruning can significantly reduce both the model's size and the number of calculations needed to run it.
Are there different ways to prune, like snipping individual wires versus cutting whole cables?
That's a good analogy. There's unstructured pruning, which sets individual unimportant weights to 0. This creates a sparse weight matrix, lots of zeros. It's great for storage size, but often needs special hardware or software to run efficiently during inference because you're dealing with all those scattered zeros.
And the other type?
Structured pruning. This is often more practical for hardware acceleration because it removes entire structured blocks, think whole neurons or attention heads in a transformer. This results in a smaller but still dense model that runs efficiently on standard hardware.
And I remember hearing about something called the lottery ticket hypothesis linked to pruning.
That sounds intriguing.
It's a fascinating idea that's really influenced this field.
Yeah.
The lottery ticket hypothesis basically suggests that within these large, dense neural networks, there exist small, sparse subnetworks like hidden winning lottery tickets.
Okay.
And if you could identify these winning tickets early on and train only them in isolation, they could achieve performance comparable to the original, much larger network. It provides a powerful theoretical reason why highly efficient pruned models are possible.
Cool. What about knowledge distillation? Katie. That sounds like one AI teaching another smaller AI.
That's exactly what it is. Knowledge distillation is like model mentorship. You take a large, powerful, pre-trained model of the teacher and use it to train a smaller, more compact model of the student. How does the teacher teach?
The student learns not just from the correct answers, for the ground truth labels, but also by trying to mimic the teacher's output probability distributions, the soft targets. It learns the teacher's nuances.
So the student captures the teacher's wisdom, but in a smaller package.
Precisely. It captures the teacher's nuanced knowledge and generalization ability in a much more efficient form. Katie is absolutely fundamental to that hybrid cloud edge strategy we talked about. It's how you transfer sophisticated skills from a giant cloud model into a specialized, edge-ready SLM.
Got it. And finally, low-rank factorization. How does that make a model smaller?
This is more of a mathematical trick that focuses on the big weight matrices inside neural network, especially in those fully connected layers or attention mechanisms. It works by decomposing a large matrix into two or more smaller, lower rank matrices.
And the product of the small ones approximates the big one.
Exactly. The product of these smaller matrices approximates the original large one, but the total number of parameters needed to store the smaller matrices is significantly less. Think of it like realizing you can build a complex Lego structure using fewer, strategically chosen smaller blocks that achieve almost the same result but are much lighter.
So these compression techniques, quantization, pruning, knowledge distillation, low-rank factorization, they're really the engine room for getting AI onto our devices, each with its own pluses and minuses.
Absolutely. They each have a role depending on the specific app and the target hardware. Quantization, great for memory and speed, ideal for phones, MCUs, but maybe a tiny accuracy trade-off sometimes.
Pruning.
Reduces parameters in compute, good for compact models on specialized accelerators.
Knowledge distillation.
Perfect for transferring complex skills from big teacher to small student, key for making specialized SLMs.
And low-rank factorization.
Directly cuts parameter count, especially useful for those dense matrix operations common in transformers.
Okay. Now, beyond just squashing existing models, the second pillar is about designing totally new model architectures that are just built to be more efficient from the get-go. This sounds like designing a lighter, faster engine from scratch, not just dieting the old one. What about mixture of experts? MOE. I feel like I'm hearing that term everywhere lately.
MOE is definitely one of the hottest and most promising architectural innovations right now, especially for scaling models efficiently while keeping the actual compute costs down.
How does it work? It's not one big model.
No. Instead of one giant monolithic model where all the parameters are used for every single input, a MOE architecture uses many smaller expert subnetworks. And there's a lightweight gating network that acts like a traffic cop.
Okay, so what does the gating network do?
For each piece of input, the gating network dynamically figures out which experts are most relevant and activates only a small subset of them.
Ah, so it's like having a big team of specialist consultants, and for any given problem, you only call in the 2 or 3 who are the absolute best for that specific thing right now. That sounds incredibly efficient.
That's a perfect analogy. It allows for models that have an absolutely enormous total parameter count, potentially trillions, but the active parameter count for any single calculation is much, much smaller.
Which means less computation.
Dramatically less computation. For example, there's a model called JetMo. It reportedly beat the much larger Llama 2 7B model on some tasks while using 70% less compute power. How? By activating only about 2 billion of its 8 billion total parameters for each token processed. It's a massive leap in efficiency.
Wow. What other architectural tricks are making models lighter? You mentioned parameter sharing and efficient attention.
Both are super important. Parameter sharing techniques, like the ones used in models like Albert, that's a Lightbert, reduce the total number of parameters by cleverly reusing the same layer parameters at different points in the network's depth. Others share embedding parameters or use tricks like group query attention.
And efficient attention. That tackles a known bottleneck, right?
Yeah, it tackles a major bottleneck in the standard transformer architecture. The self-attention mechanism has a computational and memory cost that grows quadratically O(n) squared with the length of the input sequence.
Which is terrible for long documents or conversations.
Terrible, it just blows up.
Yeah.
So researchers have come up with more efficient alternatives. Things like Linformer, which gets it down to linear complexity. Performer, which uses clever math approximations. FNet uses Fourier transforms. And models like Mistral use sliding window attention, which only lets tokens pay attention to their nearby neighbors, all drastically cut down the computational load for attention.
And then there's neural architecture search. NAS. This sounds like AI designing AI. Is that right?
That's essentially what it is, and it's incredibly powerful. NAS automates the really complex, often intuition-driven process of designing neural network architectures. It frames it as a search problem.
How does it search?
It typically involves three parts: a search space that defines all the possible building blocks and ways to connect them, a search algorithm, maybe reinforcement learning or evolutionary algorithms to explore that huge space, and a performance evaluation strategy to quickly guess how good a potential architecture is without fully training it.
And why is this so powerful for the edge?
Because, and this is key, hardware constraints can be baked directly into the optimization process. NAS isn't just searching for the highest accuracy anymore. It can find architectures that hit the best possible trade-off between accuracy, inference speed on a specific target chip, memory usage, and power consumption.
So you get models tailor-made for specific hardware.
Exactly. Bespoke, highly efficient, hardware-aware models automatically discovered for specific edge devices. It's next-level optimization.
That is next level.
Yeah.
Okay, so we've compressed models, we've designed smarter architectures, but the third pillar, hardware-software co-design, feels like where it all truly meshes together. A symbiotic relationship.
It absolutely is. The peak level of efficiency, the absolute best performance per watt, is achieved when the AI model and the hardware it runs on aren't designed separately, but are developed together in tandem.
So they influence each other during design.
Yes. This principle of hardware-software co-design is fundamental to pushing the boundaries at the edge. The core idea is creating this perfect synergy. The software, the AI model, its architecture, the optimization algorithms is designed to map perfectly onto the specific capabilities of the hardware accelerator.
And the hardware.
And the hardware is custom built to be exceptionally good at running that specific class of algorithms.
Can you give a concrete example of that co-design synergy?
Sure. Imagine designing a quantization algorithm that's software that uses a numerical format perfectly matched to the low-bit math unit supported by a new NPU, a neural processing unit that's hardware. Or maybe designing a new accelerator on an FPGA with a data flow and memory setup, precisely tailored to the unique way a novel, efficient attention mechanism accesses data. As AI workloads get more specialized and performance per watt becomes the dominant metric at the edge,
General-purpose chips just can't keep up.
they become increasingly inefficient. Hardware-software co-design is the clear path forward for creating these application-specific systems-on-chip, or SoCs, and accelerators that can deliver orders of magnitude improvements in energy efficiency. That's absolutely crucial for battery-powered devices and then next wave of edge AI.
So it's not just about picking the right chip off the shelf anymore. It's about making the model fit the chip and the chip fit the model perfectly.
Right.
And it sounds like this means optimizing across, multiple layers at the same time?
Exactly right. This shift to the edge brings this new multi-layered optimization challenge that you have to tackle holistically. At the top level, you have the system-level architectures. It's centralized, decentralized, federated. Yeah. Below that, the model architecture. Are we using a dense model or a mixture of experts? Then comes algorithmic optimization, all the compression techniques we discussed. And finally, at the base, hardware optimization, choosing or designing specialized accelerators.
And you need to optimize all four together.
You have to. A brilliant model on the wrong hardware. Inefficient. Advanced hardware running an unoptimized model. Wasted potential. They depend on each other. This interdependence really underscores why you need that full-stack, co-designed approach.
And you mentioned something called tuning-free compression as a critical emerging trend. Why is that so significant?
It's a huge focus right now. Think about it. Fine-tuning a multi-billion parameter LLM after you've compressed it, that takes a lot of time and a lot of expensive compute resources. It's a major operational bottleneck for companies trying to get products out the door.
So tuning-free avoids that.
That's the goal. There's immense R&D pressure to perfect techniques, especially in post-training quantization, that can effectively compress a model without needing that costly, time-consuming retraining loop. The companies and tool chains that master this, they gain a massive competitive advantage.
How so?
Faster time to market, lower development costs. They can deploy highly efficient models to the edge much more rapidly, getting powerful AI into products way faster than competitors who are stuck in long fine-tuning cycles.
That is a massive edge.
Okay,
so this brings us right down to the metal, the physical layer, the specialized hardware that's actually powering this whole edge revolution. What does all this mean for the chips themselves?
It means a really diverse and specialized hardware ecosystem, quite different from the more uniform landscape you see in big data centers.
Right. Unlike data centers where GPUs are king, the edge seems to have this whole zoo of specialized processors.
Well,
what's the breakdown? What are the main types of edge AI accelerators beyond just GPUs?
You'd right, the edge is much more varied. This diversity is a direct result of the incredibly wide range of needs, performance, power, cost across different edge applications.
Okay, let's start with neural processing units, or NPUs. What are they?
NPUs are highly specialized chips, ASICs, application-specific integrated circuits. They are designed from the ground up specifically to accelerate the core math operations in neural networks, like matrix multiplication and activation functions.
So they're custom built for AI math.
Exactly. By doing this directly in dedicated silicon, NPUs achieve the highest levels of performance per watt. This makes them ideal for situations where you need high-performance inference, but are constrained by power, like in smartphones or smart cameras. Qualcomm's Hexagon NPU and Snapdragon chips, or NPUs from companies like Rockchip, are good examples.
And GPUs still have a place, but they're adapted for the edge.
Yes, the massively parallel nature of GPUs, originally for graphics, still makes them very effective for the parallel math and deep learning. Edge-optimized GPUs, like NVIDIA's Jetson family, provide serious computational muscle for complex AI tasks.
Like what kind of tasks?
High-resolution computer vision, fusing data from multiple sensors in robots or autonomous machines. But they typically use more power than NPUs, so they're better suited where raw performance is the top priority and power isn't quite as tight, maybe in an industrial robot plugged into the wall.
What about FPGAs? I know those are reconfigurable, which sounds super useful for AI models that are always changing.
They are very useful for that reason. FPGAs, field programmable gate arrays, are chips with arrays of logic blocks that you can program. This lets developers essentially create custom hardware circuits perfectly tailored to a specific AI algorithm.
So you get custom hardware speed plus flexibility.
Exactly. FPGAs offer this unique mix. Low latency, high parallelism, and critically, the flexibility to be reprogrammed out in the field to support new models or algorithms as they evolve. This makes them ideal for applications where things change fast, or for demanding real-time processing like in aerospace, defense, or adaptive industrial control. The AMD Xilinx Kria K26 is a well-known FPGA platform for edge AI.
Okay. And DSPs, digital signal processors, what's their niche?
DSPs are specialized microprocessors optimized for high-throughput, repetitive math operations you often see when processing continuous streams of data like audio or video. Their architecture shines at things like filtering or fast Fourier transforms.
So they're good for...
Extremely efficient for specific AI applications like real-time voice recognition, noise cancellation, and smart assistants or communication gear. CEVA is a big name, providing DSP IP cores for this market.
Finally, at the really low end, we have AI-enabled microcontrollers, or MCUs. These must be for the tiniest, lowest power gadgets.
Precisely. These are at the extreme low-power end of the spectrum. AI-enabled MCUs integrate small, lightweight AI accelerators right onto the microcontroller chip. They're designed to run very simple inference tasks.
Like
keyword spotting, like, "Hey Google," or basic anomaly detection in sensor data. They run on tiny battery-powered IoT devices where power consumption is measured in just milliwatts. The ARM Cortex-M series processors, often paired with their Ethos-U NPU, are leaders here, powering everything from smart switches to tiny environmental sensors.
So who are the major companies actually building and supplying all this diverse edge hardware? Sounds like a really complex market landscape.
It is complex, but also incredibly dynamic. It's a fascinating mix of the huge semiconductor giants we know, specialized companies providing intellectual property, IP, and innovative startups, all targeting different parts of the ecosystem.
Okay, let's start with the big guys, the broad portfolio leaders.
You have NVIDIA, obviously a dominant force, especially in high-performance edge AI. They're extending their data center lead with platforms like Jetson, think the Jetson AGX Orin. It's a powerful GPU-centric solution backed by their mature software stack, CUDA, TensorR. It's a top choice for demanding robotics, autonomous machines, advanced computer vision.
And Qualcomm.
Qualcomm leads in mobile and low-power devices with their Snapdragon sauce. These chips use what's called heterogeneous computing intelligently, using the Cryo CPU, the Adreno GPU, and the super-efficient Hexagon NPU together. This approach is optimized for delivering sustained AI performance within the tight battery and heat limits of smartphones, car infotainment systems, and connected IoT gadgets.
And then you have the embedded and industrial specialists. focused on specific markets.
Exactly. Companies like NXP Semiconductors, they're a key supplier for automotive and industrial sectors. They offer secure, reliable processors like their IMX series, increasingly integrated with NXP's own EIQ Neutron NPU and supported by their EIQ software. It's a robust, safety-focused platform perfect for factory automation, building controls, and in-car AI where reliability is absolutely critical.
And ST Microelectronics.
ST Microelectronics is really focused on bringing AI to the mass market of embedded systems. Their popular STM32 microcontroller family is getting enhanced with AI acceleration, making it much easier and cheaper to add smart features to everyday things like appliances or industrial sensors.
And what about the specialized IP and innovators? They don't make the final chips.
Right. They provide key ingredients. ARM Holdings is fundamental here. They don't manufacture chips, but their intellectual property, their designs for energy-efficient CPUs like the Cortex series and NPUs like the Ethos series forms the bedrock of almost the entire edge ecosystem. Nearly every silicon vendor licenses ARM designs.
No.
Then you have companies like CEVA, Synaptics, Ambarella. They design and license specialized IP cores, DSPs, vision processors, or they develop highly integrated SoCs for specific niche applications like computer vision. This lets device makers add advanced AI without having to design their own silicon from scratch.
It sounds like a very fragmented market, all this diversity. Is that a bad sign? Or is there a reason for it?
It's definitely not a sign of immaturity. It's actually a necessary adaptation. This diversity is a direct, logical response to the incredibly varied constraints you find at the edge. Power limits, cost targets, physical size, connectivity needs, real-time requirements.
So different jobs need different tools.
Exactly. An autonomous drone needs a totally different hardware solution than a tiny battery-powered sensor out in a field. This reality means that if you're developing AI applications, your strategy has to be platform agnostic.
You can't tie yourself to one chip type.
You really can't. Developers need to use abstraction layers and toolkits think ONNX runtime, TensorFlow Lite, or vendor SDKs like NXP's EIQ that let them compile and deploy the same core AI model across this diverse hardware landscape. Flexibility is key.
So the main performance metric at the edge isn't just raw speed like TOPS, but efficiency. It's all about TOPS per watt.
Exactly. In the cloud, raw compute power tera operations per second, TOPS, is often king. But at the edge, the most critical number is efficiency, specifically TOPS per watt, an accelerator that delivers amazing TOTS but drains the battery in 5 minutes or overheats the device. It's useless for most edge scenarios.
So efficiency wins.
Efficiency wins. Companies like Halo, for instance, they're winning designs in markets like smart cameras, not necessarily by having the absolute highest TOPS number, but by delivering class-leading performance within an extremely tight power budget, maybe just a few watts. Their Halo 8 chip does 26 TOPS, using around 2.5 watts. This relentless focus on efficiency is what drives innovation at the edge.
Okay, so we have all this incredible tech making AI smaller, smarter, more efficient right on our devices. Where are we actually seeing it make a difference right now? Let's talk about AI in action, maybe starting with the smart factory.
The manufacturing sector is absolutely a prime beneficiary of edge AI, mostly because factory operations demand that super low latency, high reliability, and strong data security, all things edge computing delivers well.
How is it being used for something practical like predictive maintenance, preventing breakdowns?
Yeah, in predictive maintenance, you embed sensors, vibration, temperature, acoustic sensors right into the machinery on the factory floor. On-device SLMs running locally analyze that sensor data in real time, looking for patterns, detecting anomalies.
And they can predict failures.
They can predict potential failures before they actually happen. This lets manufacturers schedule maintenance proactively instead of waiting for a costly, unplanned breakdown. It significantly reduces downtime. Big companies like GE and Siemens are already using these systems in aviation and industrial plants, saving millions.
Wow. What about real-time quality control on the production line?
Traditional QC often meant delays, maybe sending images or data off somewhere else for analysis. Edge AI changes that completely. You can have high-speed cameras connected directly to on-device vision processors doing 100% visual inspection on fast-moving lines.
So they spot defects instantly.
Instantly. Defects, misalignments, contamination spotted right away without needing to send a massive video streams to the cloud. It eliminates delays and ensures quality at line speed. There's a neat case study mentioned. 42 Technology worked with pharma partners on a system for clearing production lines between batches. It runs entirely at the edge, automating safety checks incredibly quickly for compliance.
And what about robotics and automation in these factories?
Making robots smart, definitely. Leading robotics companies like Funnick are integrating AI right at the edge to enhance their industrial robots. This allows for more precise, more adaptive cutting or welding, letting robots handle more complex tasks.
And warehouse robots.
Yes, in logistics, those autonomous mobile robots, AMRs, from companies like Six River Systems, which is part of Shopify or Cartkin, they rely heavily on edge AI platforms like NVIDIA's Jetson. They process all their sensor data locally
For navigation?
for safe and efficient navigation through complex dynamic warehouses without needing constant cloud connection. It dramatically improves warehouse throughput and safety.
Okay, let's shift gears to healthcare. This is an area where privacy is absolutely critical, and real-time response can literally save lives. How is Edge AI reshaping healthcare to be more personalized, private, and proactive?
Healthcare is a perfect fit for Edge AI precisely because it demands that data privacy and real-time capability. Take on-device diagnostics, it's transformative. Performing diagnostic analysis locally, right on portable or bedside devices using on-device deep learning models. This makes diagnostics much more accessible, especially in remote areas. And crucially, it protects sensitive patient health information, PHI, because you're not sending it off to the cloud.
Can you give an example?
Sure, think about handheld infrared cameras used for screening newborn babies' eyes. An on-device model can detect abnormalities like cataracts right there. Or powerful SLMs running on local hospital servers analyzing medical images like X-rays or MRIs to assist doctors without any patient data ever leaving the hospital's secure network.
That's a huge privacy advantage. What about continuous patient monitoring using wearables?
Wearable devices, smartwatches, medical-grade sensors are getting smarter with on-device AI. They continuously monitor vital signs like ECG or blood oxygen. Personalized AI models running right on the device can detect critical events in real time,
Like a heart problem.
like a cardiac arrhythmia or maybe an epileptic seizure, and they can trigger immediate alerts, even if the device isn't connected to the internet at that moment. This shifts healthcare from just periodic checkups to truly proactive, continuous health management. It allows for much earlier intervention and better outcomes.
And for medical research, where collaboration is key but data sharing is hard, privacy-preserving collaborative research using federated learning must be a huge deal.
It is, absolutely. Hospitals and research centers have these incredibly valuable data sets, but they often can't share them directly because of strict regulations like IKEA.
So FEL provides a way around that.
Exactly. With federated learning, a group of hospitals can collaborate to train a much more powerful and robust diagnostic model, maybe for a rare cancer where no single hospital has enough data. Each hospital trains the shared model on their own private patient data, locally.
And they only share the model updates.
Only the non-sensitive model updates are aggregated. This builds a superior global model that benefits from all that diverse data without any raw patient data ever leaving its source institution. It's incredibly powerful for speeding up medical discovery while maintaining bulletproof privacy.
Okay, now let's look at finance and security. Another area where trust and data integrity are non-negotiable. How is Edge AI, especially FL, enabling a more decentralized trust model here?
The financial industry, with its super strict regulations and security needs, is definitely leaning into federated learning to build smarter systems without centralizing sensitive customer data. Take collaborative fraud detection, for example.
Fraudsters operate across banks.
Yeah, exactly. Sophisticated fraudsters often hit multiple institutions. A single bank might not see the whole pattern. Federated learning lets a group of banks work together to train a shared fraud detection model.
Each trains on their own data.
Each bank uses its own private transaction data locally. The aggregated model updates create a global model that's far better at spotting complex cross-institutional fraud patterns than any single bank could be on its own. And critically, they do it without sharing confidential customer data with each other.
That's clever. What about enhanced credit risk assessment?
Similar idea. FFL can help build more accurate, potentially more equitable credit scoring models. By training a model across the siloed datasets of multiple lenders, you can get a more comprehensive view of creditworthiness. Again, respecting privacy and the competitive boundaries between the lenders. It allows for better risk assessment without creating a central honeypot of financial histories.
Okay, let's bring it closer to home.
Yeah.
How is Edge AI impacting the intelligent consumer and autonomous systems? Our phones, our cars.
Edge AI is rapidly becoming just a standard feature in consumer electronics, and it's absolutely fundamental for any kind of autonomous system. Think about personalized on-device assistants.
Like Siri or Google Assistant, but running locally.
Exactly. The next generation of digital assistants on our phones and computers will run using on-device SLMs. This allows for truly personalized, context-aware experiences.
Such as?
Real-time transcription that understands your specific vocabulary, intelligent reply suggestions based on your past messages, proactive task automation based on your calendar or habits. It works by securely learning from your local user data, emails, calendar, usage patterns without sending that private info to the cloud. The AI genuinely gets to know you privately on your device.
So even really advanced stuff like generative AI is coming to the edge. I saw demos of Stable Diffusion running on a phone. That seemed like science fiction just recently.
It's happening now. Generative AI on the edge is a reality. Once it required powerful cloud servers, but now highly optimized versions of models like Stable Diffusion are running directly on consumer devices.
How is that even possible?
It's a combination of really aggressive model quantization, shrinking the models down, and the powerful, dedicated NPUs that are now built into modern mobile chips like the Qualcomm Snapdragon 8 Gen 2.
This enables
It enables cool applications like real-time, on-device image generation. You could create amazing visuals right on your phone, no internet connection needed.
And of course, autonomous vehicles are the poster child for needing low latency, on-device AI for safety.
Absolutely. For anything safety critical in a self-driving car or an autonomous drone, on-device AI is non-negotiable. The delay of a round trip to the cloud is simply unacceptable when a split-second decision is needed to avoid a collision.
So everything happens locally.
Yes, these systems use powerful edge computers right in the vehicle to fuse and analyze data from a whole suite of sensors, cameras, LiDAR, radar, IMUs in real time. They perceive the environment, predict what others will do, and control the vehicle. All that complex processing happens locally for immediate, reliable decision-making.
This sounds like it's creating entirely new ways for companies to compete. The old idea of a data moat was just having the biggest central pile of data. How is that changing now with edge AI?
You're absolutely right. The concept of the data moat is fundamentally shifting. In the cloud AI era, competitive advantage often came from hoarding the largest centralized data set. But in the edge AI era, a new, arguably more defensible moat is emerging. It's based more on process and active learning rather than just static data accumulation.
Can you give an example of that?
Think about a company like John Deere. They have this massive fleet of thousands of AI-enabled smart tractors operating all over the world. Each tractor generates unique, real-time data about soil conditions, crop health, machine performance right there in the field. That data is specific to the farmer. It's often private.
So John Deere can't just centralize all that farmer data easily. How do they gain an advantage?
By using federated learning across that huge distributed fleet, they can continuously train and improve a global model for optimizing farming practices. The learnings, the insights derived from every single tractor's operation are aggregated to improve the central model.
And that improved model gets pushed back out.
Exactly. Pushed back to the entire fleet, making every single tractor smarter over time. The competitive advantage isn't in a static central database. It's in having the largest active fleet generating insights and the most efficient FL pipeline to create this powerful continuous learning loop. It's a dynamic moat based on shared intelligence, not shared raw data.
That's fascinating. And this deep integration of software running efficiently on specific hardware, it seems to be driving a return to vertical integration too, companies designing their own chips.
Absolutely. Achieving peak performance per watt at the edge really comes down to that tight hardware-software co-design. Companies that can control the entire stack from the application software and the AI model all the way down to the custom silicon it runs on, they can achieve a level of efficiency and optimization that's incredibly hard for competitors using off-the-shelf parts to match.
Like Apple or Tesla.
Exactly. Look at Apple designing its own A-series and M-series chips with integrated neural engines specifically to power its on-device AI features. Or Tesla designing its own custom AI chips tailored for its vehicle's needs. As edge AI becomes more critical for product differentiation, especially in high-stakes areas like automotive, robotics, medical tech,
More companies will go down this path.
more companies will feel compelled to either design their own custom silicon or form extremely deep collaborative partnerships with semiconductor vendors to create bespoke systems on chip optimized for their specific applications. It's about owning the whole stack to get that ultimate performance and efficiency edge.
These real-world applications are clearly just the start. This whole shift to edge AI seems to point towards an even more transformative future. What's the emerging paradigm? Where is this all heading?
Well, the technology stack we've been discussing, these efficient SLMs, the decentralized communication like FL, the real-time edge processing, it's all the critical foundation for what's coming next, the rise of agentic AI.
Agentic AI, what does that mean?
It represents a really profound paradigm shift. Moving away from today's AI, which is mostly reactive or assistive, it responds to our commands towards future AI systems that are truly autonomous and proactive.
So AI that acts on its own initiative.
Essentially, yes. An AI agent is a system that can perceive its environment, reason about its state and goals, create a plan, and then execute actions to achieve those goals, often with very little or even no direct human intervention.
And these agents will work together.
That's the vision. The future edge won't just have isolated models. It will be populated by collaborating systems of these agents. Gartner actually predicts that by 2028, 15% of all edge computing deployments will use agentic AI. That's a huge jump from basically zero today. These multi-agent systems will be able to manage incredibly complex, dynamic environments in real time.
Can you paint a picture of what that might look like?
Sure. Imagine a smart city. You have AI agents running on traffic cameras, on public transit buses, on the energy grid controllers. They could collaborate to autonomously reroute traffic around an accident they detect, automatically dispatch emergency services, and optimize power distribution to handle the changing load, all happening instantly, without a human needing to coordinate it all. Or think of a smart factory. Agents don't just detect a defect on the production line. They autonomously figure out how to reroute workflows around the problem, adjust machine settings upstream, and even schedule the necessary maintenance to fix the root cause all by themselves. This is the kind of autonomous future that this distributed intelligence revolution is paving the way for.
And as all this computation and intelligence moves dramatically to the edge, it creates a new center of gravity for data, right? Along with this absolutely critical need for zero-trust security.
Yes, exactly. That old idea of data gravity, where big data piles attract applications, is definitely flipping. It's shifting from the centralized cloud out to the distributed edge.
Is there data to back that up?
Yeah, Gartner forecasts that by 2025, a staggering 75% of all enterprise-managed data will actually be created and processed outside of a traditional data center or cloud.
75%. Where is it all coming from?
From the explosion of IoT sensors, cameras everywhere, connected vehicles, personal devices, this massive flood of data is making edge locations the new hubs of digital activity. And this demands a fundamental rethink of infrastructure. You need robust local compute, storage, and networking right there to process data where it's born, because you just can't realistically ship it all back to a central cloud anymore.
And with all that valuable, sensitive data spread across potentially billions of devices and autonomous agents, how on earth do you secure it? The old castle wall security model seems totally broken.
It absolutely is. This is where the zero-trust imperative becomes non-negotiable. In a highly distributed world filled with billions of connected devices and autonomous AI agents, the traditional security model of building a fortified perimeter is completely obsolete. The attack surface is just too vast, too shifting.
So what's the alternative?
The only viable security posture is a zero-trust architecture. It operates on a simple, powerful principle: never trust, always verified.
Assume nothing is safe.
Exactly. Assume no user, no device, no network is inherently trustworthy no matter where it is. Every single request to access any resource must be strictly authenticated and authorized before access is granted, every single time. It relies on strong identity checks, breaking networks into tiny segments, microsegmentation, and constantly monitoring for suspicious activity. This isn't optional. It's the mandatory security standard needed to protect data and ensure the integrity of these future distributed AI systems.
So putting it all together, for the technology leaders listening, what are the top strategic recommendations? How should they navigate this profound shift towards a distributed, edge-native AI ecosystem?
Based on the insights in Rick Spare's paper, I think there are 5 really key priorities for any forward-thinking organization. First, embrace a hybrid multi-model strategy.
Don't bet on one giant model.
Exactly. Resist the siren song of a single, all-powerful LLM. The future isn't one model, it's a diverse portfolio. Leaders need to invest in building that internal model supply chain. We talked about taking powerful foundation models from the cloud, then using compression, fine-tuning, specialization to create a whole suite of efficient SLMs tailored for specific edge jobs. The default assumption should always be hybrid cloud edge.
Okay, number 2.
Prioritize full-stack, co-designed solutions, especially for high-value, performance-critical edge AI products. You have to move beyond thinking of software and hardware as separate things. The biggest competitive wins in performance and efficiency will go to those who master hardware-software co-design.
Which means investing in talent.
Investing in full-stack talent, yes, and pursuing deep, collaborative partnerships with silicon vendors for optimized solutions. And for truly strategic applications, developing custom silicon needs to be on the long-term roadmap.
Third, invest in federated learning as a core competency. This keeps coming up.
Because it's that important. View FL and other privacy-enhancing technologies not as niche academic topics, but as core strategic capabilities. In this world of tightening privacy rules and higher user expectations, being able to train models on distributed sensitive data without centralizing it, that's a powerful, defensible, competitive advantage. It's how new data moats will be built at the edge based on privacy and collaboration, not just data hoarding.
Number 4, build for a heterogeneous hardware future.
Acknowledge that the edge hardware market is fragmented and likely will stay fragmented. It's a feature, not a bug. So develop your software and MLOps strategy to be fundamentally platform agnostic. Use abstraction layers, standard runtimes like ONNX, flexible toolchains. Your AI applications need to be compilable and deployable across that diverse, ever-changing landscape of NTUs, GPUs, FPGAs, and whatever comes next. Don't bet the farm on one chip type.
And finally, number 5.
Prepare for an agentic, zero-trust world. Start architecting your future systems with the principles of agentic AI and zero-trust security baked in from the beginning. Design for autonomy. Design for robust communication between agents. Design for a security model that's identity-centric, continuously verified, not based on a perimeter you can't defend anymore. The organizations building these principles into their foundation today, they'll be the ones best positioned to lead in the more autonomous, intelligent, distributed world that's coming fast.
Wow, what an incredible journey we've really taken today. We started with this huge strategic pivot in AI, didn't we? Moving from those massive, monolithic, cloud-bound models
To this new era of distributed, specialized, and incredibly efficient intelligence that's popping up right at the very edge of our networks.
Yeah, and we explored how new architectures like federated learning, these brilliant model innovations like mixture of experts and quantization.
And all that specialized hardware, from NPUs down to tiny AI-enabled microcontrollers.
Right, how they're not just cool tech feats, but they're genuinely transforming whole industries. And our own personal experiences, too, making AI more personalized, more private than ever before.
This deep dive, really digging into the evolution of these edge-capable LLM ecosystems, thanks to Rick Sparrow's insightful work, it truly lays out a pretty clear roadmap for where things are headed.
Yeah.
It's obvious that AI is becoming more integrated, more personalized, and, well, fundamentally more essential to pretty much every part of our digital and physical lives.
So here's a final thought for you to chew on. As AI becomes more and more embedded, not just in our devices, but really within the fabric of our world, with these autonomous agents making real-time decisions, often without direct human oversight, what new ethical questions, what new societal impacts might pop up that maybe we aren't fully prepared for yet? How do we make sure these distributed intelligences, as they become more independent, actually stay aligned with their human values? Something to definitely mull over as you navigate this rapidly evolving, intelligent world.
Thank you for joining us on this deep dive.
We hope you continue to be as curious as we are about the evolving world of AI. Until next time.